The growing size of AI models is posing unique challenges of the cost for training and serving them. In particular, inference efficiency is now a major problem facing many AI developers. To bring AI to more people, models need to be cheaper to train and run. Increasing efficiency across various parts of the training and inference pipeline will include optimizing existing large models, but also creating new models with new architectures and new training paradigms. In this session, we will hear from 3 experts on efficiency. Song Han from MIT will talk about recent developments for accelerating deep learning training on edge devices. Yi-Chang Hu will describe the latest development of DeepSpeed, a deep learning optimization library that makes distributed training and inference easy, efficient, and effective. We will also hear from Shobu Makhraji from MSR Redmond, who will share an overview of recent research efforts for making large-scale model fine-tuning and serving more efficient.
Hello everyone, welcome to my presentation about on-device training under 256 kilobytes of memory. My name is Song Han from MIT. So on-device training is essential, where AI systems need to adapt to those new sensor data for customization and continual learning purpose. Being able to learn on-device also protects users' privacy, where we no longer have to send our local private information to the cloud, which can potentially reduce the cost as well. However, training is much more expensive than inference, especially for the memory, due to we have to do back propagation, where all the intermediate activations has to be kept in the memory for back propagation. Also, there's batch size that we need to take care of in order to make it easy to converge. So all these factors makes it hard to deploy on-device training on edge devices. For example, on a microcontroller that has only 256 kilobytes of SRAM. Prior to that, we have solved the inference problem on these IoT devices. The work is called MCUNet. So MCUNet is a co-design of neural network architecture with the inference engine. So by co-designing the tiny NAS and the tiny engine, we can achieve much better accuracy with lower cost. So for example, on the left-hand side, here's the demo. On the left-hand side, the blue curve is the baseline of MobileNet V2 plus TensorFlow Lite Micro, which can achieve about 88% top-line accuracy on the visual wake-words dataset by detecting person. So the yellow curve is our 2019 result, where we can achieve about 88% accuracy with 256 kilobytes of memory. By 2020, with MCUNet, we are able to push the memory to only 128 kilobytes while maintaining the accuracy to 90%. By 2021, we further pushed the memory consumption to only 30 kilobytes while maintaining the same accuracy. So 30 kilobytes, that is very affordable for many different tasks and very cheap devices. And the key idea is using this patch-based inference, which can drastically reduce the cost of inference. But what about training, right? How do we enable on-device training on edge devices? By utilizing existing solution, including TensorFlow or PyTorch or even the MNN, that require tens of hundreds of megabytes of memory, which is far beyond the memory constraint of a microcontroller, which is roughly 256 kilobytes. So our solution, by algorithm and system co-design, we can reduce the memory usage by more than 2000x and push the memory required for on-device training to only 149 kilobytes. So truly enable on-device training with even microcontrollers. So here we are I'm going to introduce several techniques to achieve such amazing memory reduction while fully maintaining the transfer learning accuracy. So start by introducing this tiny training engine that reduced the memory by 7.3x, followed by this quantization-aware scaling, which enables integer training on the real quantized graph, which bring about 1.4x reduction. And and another contribution here is we can fully maintain the accuracy using the quantized training. And next, we are going to introduce this sparse layer, sparse tensor update that partially selectively update the different layers, and even within a layer, we selectively update a sub portion of a tensor. So that brings about 10x speed up, 10x memory reduction. So finally, with this operator reordering, we can push the memory by another 2.8 times. So let's start with how to deal with the quantized graph. So on-device training, usually those edge devices has limited floating point units. So how do we work directly on a real quantized graph without any floating point operations? So this is a comparison where on the left-hand side is the real quantized graph, which happens during inference, and on the right-hand side is the fake quantized graph, which is used during quantization-aware fine-tuning, which usually happens in the cloud. And the purpose of quantization-aware fine-tuning is to obtain the final integer-only model. But during this process, the full floating point number is maintained in the background, right? So we maintain a copy of a floating point number during forward and backward. But this is not realizable for a real quantized graph where everything is in integer, right? We do convolution for the int8 input, int8 weight, and then we accumulate that into int32. There's no floating point in the background, right? And we add the bias, and then only here by multiplying with the scaling factor, right? So here we convert it back into int8 for the next layer, right? So here's a comparison between a traditional fake quantized graph versus our problem where we have to deal with a real quantized graph. Since the model is already trained, it is already on the model, and we have only integer only operations here. And here we have no batch normalization, since at inference time the model has been frozen and batch normalizer has been folded into the convolution layer, which makes the training very difficult, right? So the challenges include we have to deal with mixed precision, int8, int32 for accumulation, FP32 for the scaling factor, and the lack of batch normalization, which makes training and convergence much more difficult. So here is the performance comparison with naive solution, just using standard SGD compared with FP32 training. The int8 fine-tuning, actually this is fine-tuning, the int8 fine-tuning will lose more than 10% accuracy, averaged over 10 data sets for fine-tuning. So what is the problem here? How do we make it possible to to fine-tune the model on a real quantized graph rather than a fake quantized graph? So we try to understand why is the training convergence is getting worse. So here we plotted the log of W over gradient, the weight over gradient, to see what happens for this ratio. So for different tensors, the FP32 ratio is pretty low and flat. But for this int8 ratio, W over G, for different layers, for weights and biases, the fluctuation is huge. So here, this is 5 orders of magnitude difference, since this is the log scale. So why did it, the scale of the weight and gradient does not match? So we are trying to figure out what is the issue here. So we have to deal with the derivation of this quantization process, where this W hat means it's the int8 version, X hat is the int8 version of the activation, and B, the bias in 32 is the quantized version of the bias. So here we multiply that by a scaling factor and cast it so that we can get the final in-8 version of the activation. So therefore, if we use this W hat to represent the quantized weight, so S is the scaling factor, the floating point weight actually equals to this scaling factor that projects between this minus 127 to plus 128, all the way back to from minus 128 to plus 127 projected back to the original min and max, okay, using this scaling factor. So according to this chain rule, so the gradient over this W hat, okay, will be equal to SW times the gradient of this original W. Okay, so far so good. But what happens if we measure the proportion, the ratio of weight over gradient? Why this matters? We want to make sure for different tensors, the weight over gradient, the ratio is roughly the same. Otherwise, for certain layers, if the gradient is too large, the optimization either too large or the gradient is too small, the optimization will be not stable, right? So when we are calculating after quantization, what is the ratio between this quantized weight versus the gradient with respect to this quantized weight? So we actually plug in this W, which equal to the original W divided by the scaling factor, and the gradient to the quantized W, okay, is actually equal to the scaling factor times the original GW. So finally, we can find actually there's a term SW minus to the power of minus 2 of the original weight over gradient. Okay, so after quantization, there is a term due to the chain rule. It's the scaling factor to the power of minus 2. Okay, since the scaling factor is different for each channel and for each layer, and this makes the training highly unstable. Okay, it perturbs this ratio between W over G. Okay, therefore we want to rescale the gradients. Okay, so this tilde GW hat, we rescale that by SW to the power of 2 to offset the SW to the power of minus 2. Okay, this GB, similarly, we want to scale it by the same scaling factor. So what about the new ratio between the W over G after applying such scaling factor to factor away the scaling factor? Okay, so here we observed that after applying this quantization aware scaling, basically we are scaling the gradient and also we are scaling the weight, the bias by SW to the power of minus 2. So here we find after QoS, the weight over gradient can almost fully match the original ratio, okay, rather than this zigzag version of the int8 version. Okay, so the int8 plus QoS can almost match the original FP32 version. So this quantization aware scaling addresses this optimization difficulty, right? So if we just use a naive SGD, the accuracy degrades by 10%. Even the LARS, which is the layer-wise adaptive learning method, cannot converge very well. And using the Atom solution, still have accuracy loss, and it has to maintain an extra memory of up to 3x in order to store those the state tensors, in order to calculate the state, maintain the state of the Atom optimizer. Okay, so using our solution, using the int8 plus the quantization aware scaling, we can use just 1x, the original, the same amount of memory with SGD, but maintaining same level accuracy, sometimes even a little better compared with the FP32 SGD for fine-tuning. Okay, so quantization aware scaling is an effective method enabling fine-tuning on a real quantized graph. All right, so that's the first technique. The second technique is called sparse layer and sparse tensor update. So compared with full update, we initially tried bias-only update in the paper called TinyTL, Tiny Transfer Learning, which was published in NeurIPS 2020. in that paper we find is actually very effective just to fine-tune the bias without fine-tuning the weight, which can give a decent amount of accuracy, but doesn't require to store any intermediate activation at all. Since during backpropagation, the chain rule says if you're not updating the weight, you don't have to store the activation at all. But we find that actually sometimes hurt the model capacity and accuracy since you're not updating any weight. Now we use an intermediate solution. So here we find that we can partially update different layers, including the weight and also the bias. Okay, not all the layers are equal, right? We can select a subset of the layers to update. And we propose an automated approach to automatically select which layers need to be updated and which layer we can just keep them the same. So we don't need to store any intermediate activation. And further, going one step further, we can enable this sparse tensor update. So even within a weight tensor, we can only partially update, say, the first one third or the first 3/4 of the weight. And the remaining of the weights are kept the same so that the corresponding activations doesn't need to be stored in memory. So here on the bottom is the comparison of this dense backpropagation versus sparse tensor backpropagation. Okay, during the dense version, when we are calculating dydx, dydw, we have to store all the activations, right? So here, for a sparse tensor update, since we are only updating the partial weight, okay, so this is a partial dw we want to update. So it corresponds to only a partial of the intermediate activation that we need to store in memory, right? So rather than storing the whole activation in the memory, since we only need to update the first 1/4 of the weight, therefore we need to only store the first 1/4 of the activations, which can save the activation, okay? Which is a critical bottleneck and key differentiation factor from inference to training. So let's see how that works. We can imagine different layers have different contribution to the accuracy, right? So here we plotted the number of layers to update the bias versus the relative accuracy gain, okay? So for the bias update, we find the accuracy actually goes higher as more layers are updated, right? But it plateaus very soon, okay? So for example, after updating 25, 26 layer, it almost plateaus. So it's enough to just update the 25 bias layers, okay? And for the weight update, we find that those later layers contribute more to the accuracy, right? Of course, there are two versions. Update all the channels, half of the channel, 1/3, 1/4, 1/8 of the channels. So we find the more we update, the higher the accuracy. And also the later the layers, the higher the accuracy. And also the first point-wise convolution contributes more. And then the depth-wise doesn't contribute more. And the last point-wise layer contribute less. This is actually a good observation due to the inverted bottleneck. The expansion ratio is 3 or 6, which is pretty large for the intermediate depth-wise layer. So we don't want to update that one. But updating this, the first point-wise layer is very efficient since the number of channels before that is pretty low. So we need to store less number of channels. And then we want to automate this process by this contribution analysis. So here are all the layers. So altogether we have more than 40 layers in this MCUNet. Okay, and then we are going to see what is the activation memory. So activation memory actually decrease with the layer number, and the weight actually increase with the layer number. Since the resolution is getting lower, so the activation memory is lower, and the number of channels are increasing, therefore the weight memory is increasing. So a sweet spot is actually the middle layers, where the activation and the weight is not too large. We can afford to store those intermediate activations, and we don't need to update a lot of weight, just like the later layers. As a result, our contribution analysis find the optimal solution to update. This is layer like 21, 24, 27, and 30. Okay, they are fully updated due to their weight size of the weight is relatively small. But in the later layers, since they contribute a lot to the accuracy, but the number of weight is also large, the policy find actually we can use sparse tensor updating 1/8, 1/4 of those 2 layers. Okay, so in the end, we only update these 6 layers plus the last layer. Okay, only 7 layers altogether, and 2 of the layers are partially updated. For the remaining layers, those have a very high activation cost. You see the activation is pretty large, therefore we are not updating the weight at all, right? And for these layers, we are going to update the bias since it has low activation cost, and we don't need to store these activations if the weight is not updated. So let's see, what is the memory saving and the accuracy implication? So we actually find it's pretty well maintained. The accuracy can reduce the memory by 4.5x, 7.5x, and 7.1x on different networks like MCUNet, MobileNet V2, and the proximate NAS. So very effectively reducing the memory while fully maintaining the accuracy. So last, we propose this tiny training engine further reduces the overhead. So previous DL training, the computation graph is constructed in the forward pass, and an autograd engine computes the backward graph, and the execution engine does the detailed execution schedule. And the entire backpropagation, including computing the backward graph, is happening at runtime, which is very redundant. We want to push the runtime to compile time, which is the major novelty here. Since runtime is heavy, AutoDiff at runtime is a waste of time. It has heavy dependencies and a large binary size, and these operators are optimized for the cloud, not for the edge. On the other side, the memory is heavy since there are a lot of intermediate unused buffers, and has to compute the full gradient, which cannot fully utilize our algorithm inventions, including sparse layer and sparse tensor update. So here we push the majority of the operation into compile time, and only the final executable binary for training, we push that into runtime. Okay, so tiny training engine separates the runtime and compile time, and offload most of the workloads like AutoDiff, graph optimization, and perform the tuning into the compile time. Thus, the overhead of runtime is greatly minimized. Okay, so here we have we start with a forward IR, and then we generate the backward IR. It is still flexible, right? But everything is generated at compile time. Okay, so at a runtime, we just need to execute the already compiled binary. Okay, and also we have a bunch of graph level optimizations that are applied at compile time, including folding the constant, data code elimination, and sparsify the gradient paths, supporting sparse layer, sparse tensor update, inline function, and also operator fusion. So here is our sparse update scheme. So for those bias only updates, so we specify the need gradient to be false. Then that weight will be ignored and will not be calculated for that layer. And also for the sparse tensor update, where we are not updating certain layers, we just set it both the weight and bias need gradient to be false. And then for the layers where we need the sparse tensor update, we specify need grad to be 0.5, meaning that we just need to only update the tensor partially. And we can slice away those redundant tensors and keep them the same without having to store the activation in the memory at all. So these are co-designed with our algorithm so that the sparse layer and sparse tensor update can be efficiently supported in the compiler and don't require any execution at runtime. So here is the result of the full update versus the sparse update versus the sparse update plus this reordering. Reordering means as soon as we compute the gradient, we are going to apply the update so that we are going to minimize the life cycle of that tensor. Okay, so this is measuring 3 neural nets and BV2, proximity snaps, and MCUNet. We can see there is an almost 22 to 28x reduction from this sparse update versus, and also the reordering. The majority of the saving comes from this sparse update. And here is showing the memory saving, again with the full backpropagation with the sparse update. Those are using TensorFlow Lite, and on the right-hand side is showing our own training engine called TTE, Tiny Training Engine, which we optimized our own kernels using loop unrolling, and also tiling, and also in-place steps-wise image to column, and all different advanced compiler techniques. Okay, and altogether we can reduce the peak memory by 22 to 28x. By the way, the full update of this proximity snaps movement V2 is not supported on TensorFlow Lite because it will be out of memory on the microcontroller. All right, so finally we performed this operator cycle analysis, right? So remember we performed this reordering and an in-place update, right? So therefore we can minimize the life cycle of those redundant operators. So some of this x-axis is the operator index, and the y-axis is the memory footprint. So the peak memory is bounded here versus a lower point after this optimization, where by fusing the operators and apply this in-place gradient update, we don't need to store this gradient all the way to the end. But as soon as we get the gradient, we immediately apply that gradient to the tensor rather than having to wait for all the tensors to finish. So in that way, we find this reordering and in-place update can bring about 2.8 to 3.1x reduction of the memory. Okay, so the gradient, by reordering, the gradient update can be immediately applied. The gradient buffer can be released immediately earlier before the full backpropagation happens. All right, so this is a high-level comparison of previous training infrastructure versus the tiny training engine, the TTE. Okay, so conventionally, a lot of the stuff happens at a runtime in red. Okay, only the forward graph is computed at compile time, while the backward graph and everything happens at the runtime. But now we push a lot of stuff to the compile time, and the runtime becomes very lightweighted, and also enabling sparse tensor and sparse layer update. And finally, we have a demo showing that we can actually achieve on-device training at this microcontroller that has only 320 kilobyte of SRAM and only 1 megabyte of flash. Initially, the model is randomly initialized. We have a microcontroller, have a camera pointing to the to an image. Initially, it's wrong, classifying the zebra as a person. And then we are going to apply a few more images to see actually all the predictions are wrong because the model is randomly initialized and they are not trained, so it cannot perform well on the downstream task. And we want to keep all the update, all the learning process locally on this microcontroller, so that it preserves the privacy and reduces the cost. Okay. So after the initial testing, we are going to perform on-device training. So the inference is about 3.3 FPS. The training is about 1.8 frames per second. So here we are going to do the backpropagation here. It selectively update certain layers and different portions of each tensor. And we fast forward this a little bit. So after a little while, it can train on a bunch of images. And finally, the training completes. We're going to test it again So the person is correctly classified, no person scenario is also correctly classified, and FPS is about 3.2. So you can use this person detector for your smart home. All right, to summarize, today we talk about on-device training. It is very essential to enable these IoT devices being able to not only run inference, but also to do those locally for this on-device training. It reduces the cost, preserves people's privacy, and can make the product more customized for different customers' taste. Okay, and enable this kind of continual learning and on-device lifelong learning locally on these edge devices. And for future work, we plan to not only enable vision, but also those language and more applications to enable on this device training on different modalities and different tasks. All right, more about this work can be found at mcunet.mit.edu. Thank you.
Hello everyone, this is Yuxiong He from Microsoft. Today I will be talking about DeepSpeed transformations. DeepSpeed is an open source deep learning optimization library for speed and scale. By transformations, we'll be focusing on the changes and the new directions DeepSpeed is embracing. Let me start with a bit of a recap to share the context. We initiated DeepSpeed project early 2020, about 2 years ago. In these 2 years, one biggest growth on deep learning area is the size of the model. As shown in the figure, the largest trained dense models have grown over 240 times. However, in the same duration, single GPU memory has only increased by 2.5 times. Such growth in model size has been made possible mainly through the innovations and advances in training software. DeepSpeed has been an active innovator and contributor for that. Our technologies like zero 3D parallelism and zero infinity offer system capability of training 4,000 times bigger models, powering unprecedented model sizes. Because of these and many other innovations we developed, DeepSpeed gradually becomes a popular deep learning library for large-scale training. Our open source software have also powered many advanced models. DeepSpeed has been reshaping large model training landscape, turning more ambitious models from infeasible to train to feasible and efficient to train. Moving forward, we'll continue to push for skill and speed for DL training. But what's more? It's time to embrace new challenges, bigger scope, and broader impact. We are working on an important transformation to bring DeepSpeed to next stage. Specifically, we are growing DeepSpeed from a DL training optimization library into a multi-purpose deep learning optimization suite. Training will continue to be an important pillar under the suite. But while we can train the large advanced models, how can we serve them? We have heard so many inference challenges to deploy large models from our users. It's critical to have an inference pillar optimizing inference latency and cost of these advanced models. The third pillar we recently invest is compression. It uses condensed forms to represent, store, communicate, and compute, which reduce model size, total work, and resources needed. We develop novel compression techniques and build software library to easily compose them. By combining compression that reduces total work with efficient training and inference system that accelerate the processing of the work, we hope to offer the maximum speed and cost optimization for both inference and training. This is the main transformation we are working on, growing DeepSpeed from a training optimization library towards a multi-purpose optimization suite. Next, we'll look into the new pillars, starting from inference. The deep learning inference landscape is diverse. With respect to model size, it goes from millions to billions and even trillions of parameters. With respect to model architecture, many are dense, while the new MOE-based models are diverse. Given the variations in model size, the inference hardware can be a single GPU, a single node with multiple GPUs, or across multiple nodes. And production workloads can be latency sensitive with small batch size, or throughput oriented with massive batch sizes. To tackle the diverse workload requirements, we create a systematic composition of a comprehensive and diverse set of optimizations that can cover the broad inference landscape. At the core, we have the inference-optimized transformer kernels, designed to achieve best single GPU performance at all batch sizes for models that fit in a single device. To support larger models beyond a single GPU, we build our many GPU dense transformer layer on top of the kernel layer. This layer optimizes for parallelization efficiency and reduces communication overhead as we scale across multiple GPUs within a node or across nodes. Furthermore, we have a sparse model optimization layer built on top of the previous two layers. It supports sparse components of massive scale MOE models, and is capable of real-time inference of such models with trillions of parameters. Through this systematic composition, DeepSpeed inference achieves SOTA latency and throughput across the entire inference landscape. Beyond speed and scale, we also develop new technology, zero inference, to democratize large model inference. Zero inference adapts zero infinity from training to inference. It leverages CPU, GPU, and NVMe memory to support running 50 times larger models on single GPU devices. It empowers everyone in need to try out much bigger models, even when they have limited GPU resources. These are some of the highlights of DeepSpeed inference. Next, I'll talk about our newest pillar, DeepSpeed compression. According to our user feedback, they have pressing need to leverage compression to reduce inference latency and cost further. However, they face two main challenges. First, it's hard to systematically compose different compression techniques for the best outcome. Second, there also lacks efficient inference system to execute compressed models. To help address these challenges, we start DeepSpeed compression library. The goal of the library is to help our users to compress the DL models to deliver much smaller size, faster inference speed, while drastically shortening the compression time. Inside the library, we have two main components to address the challenges we talked about. The compression composer automatically compose different techniques to get highly compressed model checkpoints. And the inference engine provide highly efficient implementation to run the compressed models faster and cheaper. Building the whole library is a significant effort. We are taking it step by step. As the first step, we focus on developing the compression composer, and we release it first version this July. Our compression composer supports a rich and powerful set of compression techniques such as quantization, sparsity, low-rank decomposition, and distillation. It allows our users to easily combine them for best compression outcome. Beyond software capability, we also introduce new compression schemes. For example, XTC offers extreme compression to reduce the model size by more than 50 times through a combination of lightweight layer reduction and binarization techniques. Another cool feature is zero quant. It offers int8 quantization with close to zero compression cost and without requiring any training data. We hope that DeepSpeed compression will help close the gap between what's possible in AI and what's deployable in your user applications. To conclude, we are on a journey of growing DeepSpeed from a training optimization library to a multi-purpose DL optimization suite with training, inference, compression, and even more capabilities along the way. During the transformation, the need of our users always get the directions we're heading towards. If you have any feedback, please don't hesitate to contact us. Together, we hope to make DeepSpeed a useful tool and a powerful enabler to help achieve your AI ambitions and missions. Thank you.
Hi everyone, my name is Shubhabrata Mukherjee. I'm a principal researcher at Microsoft Research Redmond. Today, I'm going to talk about efficient inference for large-scale AI. This is a joint work with several of our collaborators and interns. Large-scale language models have been growing exponentially over time by as much as 10x every year, which makes them difficult to use in practice. Our research aims to increase the efficiency of large-scale AI focused on three primary aspects. We want to accelerate the adoption to bring the power of AI to more and more people and go from low-code to no-code AI development. Large-scale models are also difficult to use because of their size and slow for inference. We have been developing techniques for faster inference and reducing the memory footprint. Finally, all of these techniques also contribute to reduced carbon emission, as we are looking to reduce the embodied carbon per unit inference. In this talk, I'm going to talk about two representative methods towards efficient inference. The first one is going to be about autodistill for variable language model compression. The second topic is going to be about atomics for parameter efficient tuning of large language models. So let us dive into the details. Knowledge distillation techniques transfer knowledge from a large teacher model to a small student model. These students are typically hand engineered, which requires several trial and error. They also require pre-specified compression rate. Therefore, for every time there is a computational budget change, one needs to rerun the distillation process. However, different target devices have different resource constraints. For example, CPU, GPU, and FPGAs have different memory and latency requirements. Enter autodistill. With autodistill, we generate a gallery of pre-trained edge-compressed models with massive inference speedup. Given an end device with a specific computational budget, we can just pick a model from this pool and only fine-tune on the downstream task without any additional retraining. Autodistill training has three main stages. First, we partition the transformer search space into different subspaces. Each subspace consists of several small transformer models of various sizes. Then we learn a super network for each partition via weight sharing of the student models residing in that partition. Search space partition reduces gradient conflicts arising from co-training subnetworks of very different sizes. Autodistill searches over standard transformer configurations like the number of layers, number of attention heads, and hidden dimension, corresponding to different partitions like tiny, small, and base, which we partition based on the number of parameters and flops shown in the last two rows of this table. We also leverage some inductive bias to perform this search space design such that deeper and narrower subnetworks are preferred over wider and shallower ones due to their representative capacity. Second stage of autodistill is training the super language model for each partition. We perform this via task-agnostic knowledge distillation. The term task-agnostic is important because NAS is expensive and we want to do it only once and reuse these trained student models for every task under the pre-train and fine-tune paradigm. Here, we use self-attention relation distillation to align the attention states of the student model to that of the large teacher model. Once the super language model is fully trained, the subnetworks are trained as well. Now, given a target device constraint, we can simply pick the student with the least task-agnostic validation loss that satisfies the computational resource constraint by simple lookup. Here on the left-hand side figure, we see 3-point clouds showing the different partitions corresponding to tiny, small, and base partition of the large teacher model. Each of these blue network is a subnetwork which is fine-tuned on the MNLI task and extracted from the large super language model for the corresponding partition. The red point shows the corresponding optimal auto-distill models for each partition. We observed that given any SOTA compressed model, auto-distill can always find a student with better trade-off in terms of flops versus accuracy. On the right-hand side, we see the configuration of the student models discovered by auto-distill. If we contrast these architectures with the manually hand-designed architecture in any SOTA method like the mini-LM, we straightforward see the difference between the hand-engineered versus the optimally discovered architectural configurations. Now we will shift gear and move into parameter-efficient tuning with Atomics. In the previous work, we focused on reducing inference latency, where we saw some performance regression of the small student models with regard to the large teacher model. In this work, we are going to focus on reducing the serving cost of these large language models. Here, the goal is to freeze the task-agnostic language model and inject small amount of task-specific adaptation parameters that are only fine-tuned during training. The advantage is that there is massive reduction in the VRAM consumption during training. We do not need to store the optimizer states for the frozen model, and we just need to keep one copy of the shared frozen task-agnostic language model plus some additional task-specific adaptation parameters. There are several approaches for parameter-efficient tuning like adapters and LoRa, both of which leverage low-rank decomposition modules that are updated during training while keeping all the other model parameters frozen. Adapters, for example, introduce feed-forward up and down projection modules in every transformer layer. The bottleneck dimension regulates the adapter capacity and also the number of tunable model parameters. Atomics extends this idea to mixture of adaptations. Instead of using just one adaptation module, Atomics introduces multiple modules to obtain different views of the task. Multiple modules increases the adaptation capacity. However, to reduce the computational cost like flops, Atomics leverages ideas from mixture of experts and stochastic routing to sparsely update these modules. This results in the same amount of flops as a single adapter design for top one module selection, but with increased capacity. Similar principles can also be applied to LoRa matrices A and B. Atomics leverages random routing from Thor, so there is no need for load balancing. It also does not require any additional parameters at the switch layer for module selection. Stochastic routing enables the different adapter components to learn different transformations and obtain multiple views of the task. However, there is a challenge during inference. Since we are using random routing during training, which one of these modules do we use during inference? Atomics resolves this with two key contributions. The first is consistency regularization. Here, we perform two stochastic forward passes to the network for every input batch, which activates different sets of adapter modules. We leverage consistency regularization on the module output, which enables the adapter components to share information and prevent divergence. The second key technique leverages adapter merging via weight averaging to collapse multiple views to a single view. This results in the same amount of flops and the same computational cost as that of a single adapter design. Further, we demonstrate connections to this with Bayesian neural networks and model ensembling thanks to the weight averaging idea. Here on the x-axis, we show the number of tunable parameters of different parameter-efficient tuning approaches. On the y-axis, we show the glue average performance. The red line shows the full model tuning performance, where we use Roberta large encoder, which has 355 million parameters. We observe that Atomics is the first parameter-efficient tuning approach, which outperforms the full model tuning performance while using only 0.8 million tunable parameters, which is almost 0.23% parameters of the large language model. Further, we show that similar results also are valid for natural language generation tasks, where we replace Roberta large with a GPT-2 encoder. We extend Atomics to few-shot learning, where we replace fine-tuning with prompt-based fine-tuning, keeping the Atomics architecture and training the same. We demonstrate that Atomics with only 14 million tunable parameters can outperform the full model prompt tuning performance with access to only 30 training labels for each task. Finally, to summarize, in this talk, we focused on two representative methods for efficient inference. The first one is auto-distill, which leverages neural architecture search to generate a gallery of fully trained compressed models of variable flops with as much as 41x inference cost reduction. The second technique is Adamix, which leverages mixture adaptations and sparse routing to massively reduce the serving cost. By tuning only a small amount of model parameters, Adamix outperforms full model tuning performance for both NLU and NLG tasks. You can find the reference of all these works in my homepage. Thanks a lot for your attention.